Okay, first of all, you can ignore the equipment that's sitting all around you. That most of it's for the class that'll be in here at 2:30, and some of it is for you guys for Friday, but none of it is anything for you to do today. The last thing I wanted to do for section 2 is at certain points in the course, I get to where I say to myself, you know, doing yet another example has kind of diminishing returns. I've already kind of showed you how to do some of this stuff. And if I just turn around and say, are there any questions? Everybody just sits there and says, nope, we're good, no questions. But if I say, okay, here, you do this, then I get questions. So the example at the end of section 2, or example 2-8, I would like you guys to work on that, but it makes sense to me to do this at the end of the period because, you know, some people will do it. I'm going to give you about half an hour for it. Some people will be done in 20 minutes, and why shouldn't they just be able to leave then? So we'll get back to that soon, but for the beginning part of the period, let's start Unit 3. So everything in section 3 is sort of revolving around Gauss's law. A little background information. Electromagnetism basically comes down to 4 equations, okay? With a really sharp pencil. Well, the last 2 weeks of this course are about thermodynamics, but aside from that, you could kind of say that everything you're going to spend several months trying to study can really be summarized if you had a really sharp pencil and a little piece of paper about the size of a postage stamp, okay? What physics is basically about is understanding what are the fundamental principles, of which there aren't very many, and then how do various special cases follow from those basic principles, which is what we spend most of the time on in here. So Gauss's law is one of those 4 basic equations of electromagnetism, usually called Maxwell's equations, because they were kind of all compiled by James Clerk Maxwell about 150 years ago, maybe more like 160 now. Maxwell is sort of the number 3 guy in physics behind Newton and Einstein. Like, you know, well, what Newton did for mechanics, Maxwell did for electromagnetism. Newton pulled together the various discoveries of the people who went before him, like Kepler and Galileo and so forth, added some original discoveries of his own, and that filled it out into a comprehensive description of mechanics. Maxwell took the isolated discoveries of people who went before him, like Gauss and Faraday and so on, and added some original ideas of his own, and that rounded things out to a complete description of electromagnetism. But anyhow, that's background information. What I want to do right now is introduce an idea called electric flux, because flux is a quantity that appears in Gauss's law. So for sort of an analogy, I think one of the problems people sometimes have in a course like this one is that it's less tangible than Physics 131 was. You know, last fall, the question is that a ball's rolling down a ramp and you're going to predict how fast it's going at the bottom, and that's something you can look at and touch. And now it's all about fields and currents and all this invisible stuff that you can't see and you can't touch. So having some sort of analogy to compare to can be kind of helpful. So I kind of look at it this way. Let's say you've got a balloon, just a balloon full of air hanging on the end of a string, and you turn on the shower in your bathroom. So there's all these little drops of water spraying out of the shower head, and you hold the balloon in front of the shower head, and the impact of all those little drops of water is going to push the balloon away from the shower head. In a kind of a similar way, if you have, I still got it in the drawer here, if you have an electrically charged pith ball and you hold it near another electrically charged object, like charges, it will be pushed away, just like the balloon is pushed away from the shower head in your bathroom. So something comes from the shower that pushes the balloon away. Something comes from the charged object that pushes this pith ball away. Sometimes what you're interested in is how much of that stuff passes through a certain area, okay? And that's what electric flux is, like it says there in the handout. The amount of field stuff, whatever that means. If you want a better explanation, you kind of have to get into quantum field theory, which we're not. But the amount of the field stuff passing through some area A, maybe an area bounded by a loop of wire, okay? You've got a metal coat hanger, and you hold it in, well, hold it in front of a shower head, you hold it in an electric field. How much stuff passes through the area enclosed within that piece of wire? This depends on three things, basically. If it's water in a shower that you're talking about, it depends, first of all, on how hard it's raining, okay? If you've got one of those high efficiency shower heads where you have to stand there for like 10 minutes before you get rinsed off, you're going to have less water pass through that area than if you had a regular shower head, all else being equal. And in a similar way, in a strong electric field, you have more flux passing through a given area than you would in a weak field. Another factor is how large of an area is it that you're talking about. If you have a little bitty loop of wire and you hold it in the spray of water, it's going to catch less water than if you've got a big loop of wire, all else being equal. So the strength of the field, the area, and finally how the area is oriented. If you've got your coat hanger or whatever it is, and you're holding it edge on to the oncoming water droplets, nothing passes through that loop, no matter how hard it's raining, no matter how big it is. You're going to get the maximum passing through there if the water is hitting the coat hanger face on. And at in between angles, you'll have in between amounts of water pass through there in a given amount of time. In the same way, the amount of flux passing through, electric flux passing through some area depends on how the area is oriented relative to the field. So if you put it all together, the usual symbol for flux is the Greek letter phi, capital phi to be precise. I'm going to put an E subscript on it because later in the course we'll be talking about magnetic flux when we get to magnetic fields. A lot of times I'll just leave the subscript off when it's clear from the context that I'm talking about electric flux because, well, you know, it's just a nuisance to put subscript on things if people know what you're talking about anyhow, but how much field stuff passes through some area. The strength of the field, the area, the bigger it is, the more flux it catches, and the cosine of the angle between them. People like to get the flux, they like to get phi and E confused with each other sometimes. So you write a couple of words distinguishing them underneath here. If you're drawing pictures, the flux is the density of field lines. I'd already mentioned that a week or two ago. I guess it would be two because this is only the start of the third week. But when you draw a picture of a field where the field lines are close together, the field is stronger. Where the field lines are farther apart, the field is weaker. Okay? This, of course, is just sort of a way of representing the field. Again, unless you want to get into quantum field theory, the field is actually a continuous thing. It's not actually broken up into discrete lines, but that's how we draw pictures of it anyhow. So that's the strength of the field. The flux is the total number of lines. You've got some area A. The total number of field lines passing through that area is the flux. The field strength is the flux density. If you take this definition and rearrange it a little bit, well, assuming you've got it at the optimum angle where the cosine is 1, E is equal to phi divided by A, the flux per unit area. So the field strength sometimes gets called the flux density. The denser the flux, closer together the field lines are, the stronger the field, and therefore the harder it would push on some test charge like this little pith ball here. Well, I'm not done introducing this. Let's introduce a more compact notation, because physicists seem to like to write things in really, really compact ways. You might notice this looks kind of like a dot product. A dot product of two vectors is the magnitude of the one vector times the magnitude of the other times the cosine of the angle in between them. So that kind of suggests introducing an area vector. I remember when I was a student for a short time being a little surprised by this. I mean, how can an area be a vector? It seems like if your backyard is half an acre, it's just half an acre. How does that have any kind of a direction? Well, when you're talking about people's backyards, I guess you can pretty much assume it's always pretty much horizontal, but so direction wouldn't come into it. But in general, like if I'm talking about the area of this sheet of paper, where a direction comes into it is how it's oriented, okay? Having the area like this is different than having the area like that, is different than having it like that. The area vector is defined to be normal to the plane containing the area. I'll try and draw a picture of that up there. So that's supposed to be my piece of paper, kind of looking down at it at an angle. And like I was just trying to illustrate with that pencil, the area vector is perpendicular to the plane containing whatever area it is you're talking about. So the magnitude of this vector is the amount of area enclosed within whatever shape you're talking about. If you're using SI units, that would be how many square meters. For its direction, the direction of the vector is that it's perpendicular to the plane containing the area. And so another way of writing the same thing as I did back here on the left is to say it's E dot A, the scalar product of the field vector and the area vector. For most purposes, this is what we'll use as the definition of electric flux, but I should mention that it's not the most general way of defining it, because what if the electric field is not constant all over the area that you're talking about? If it varies either in strength or direction, what you have to do is, oh, here's another picture. So maybe that's a rectangular area again that you're kind of, it's the old thing about I'm trying to draw a three-dimensional picture on a two-dimensional surface. So that's not supposed to be a parallelogram. That's supposed to be the sheet of paper and you're kind of looking at it at an angle is the idea. If you have a non-uniform field, non-uniform either in strength or direction, what you have to do is divide it up into small enough pieces that the field is pretty much constant on any given little piece. Each piece, like that one right there, for example, has an area that I'll call dA. Again, the area vector is perpendicular to the plane containing the area. E dot dA is the flux through each of these little subdivisions. You have to add those up to get the total flux through the entire area. But of course, that's just an approximation as long as it's a finite number of finite sized areas. The approximation becomes exact if you take the limit of infinitely many, infinitely small pieces. So the most general definition for electric flux is that you integrate over the entire surface. This is meant to indicate what the limits of integration would have to be. What the limits you choose have to be such that you cover the entire surface, no more, no less. E dot dA. And this version that I've written above it follows from that as a special case, okay? If the electric field is constant, well, if E is constant, you can take it out in front of the integral, which leaves you with just the integral of dA, which would be A. And that gives you the thing in the box here. So this is a special case of that. This is the general definition. This is what we'll be using most of the time. And I think I've got just enough time to run through that first example there, number 1. And then I'll, like I said, spend the rest of the period having you do problem 2-8. Like I've done several times before when we were reviewing for exams, I've written out solutions. I mean, the question has like 5 different parts. It would be fairly time consuming to go over it on the board. And so I've just printed it. And you're in luck. You don't have to read my handwriting. One of the things I did to get ready for this year is I redid it where it's all typed instead of the terrible stuff that I usually make you look at. So the idea is work on it, ask me questions, grab one of those on your way out unless you don't feel you need it. But first, the idea here is, so maybe you got a piece of cardboard just like this one, and you get a razor blade and you cut a rectangular hole in it, which is 2 centimeters long and 1 centimeter wide. And then you hold this in an electric field whose source is somewhere beyond the edges of the picture. We don't really care where the field came from, just that it points in the direction shown and has a magnitude of 500 volts per meter. Top view, that means you're looking at the piece of cardboard like this. Down here in the side view, you're looking at it like that. Well, flux is E dot A, which from the definition of the dot product means E times A times cosine of theta. We used the dot product last fall. The first place it came up was for the definition of work, where it was the dot product of force times displacement. Fill in the numbers. E, 500 volts per meter. Area. That's a rectangular area, length times width. Of course, you don't want to leave it in centimeters because that won't play nice with the meters on this other number. So 0.02 of a meter times 0.01 meter. Length times width is area. So far, very straightforward. The one trick in this question is what to fill in for theta. What a lot of people would probably do is they'd say, oh, I need an angle for theta. And they look at the picture. Oh, there is an angle. It's 30 degrees. Gotcha. Theta is the angle between the field and the area vector, okay? Like I was saying back here, the area vector is perpendicular to the plane containing the area. So the plane containing the area would be the plane of this piece of cardboard. The area vector points, well, you could think of it as pointing down or you could think of it as pointing up. It doesn't make any difference because the cosine of 60 degrees is equal to the cosine of 120 degrees anyhow. There are some situations where it's more clearly defined whether the thing points the one way or the other. But anyhow, like I said, in this case, you could think of it either way. It doesn't affect the answer. But the point is, if if the area vector points that way, if you've got 30 degrees from a horizontal line, you've got 60 degrees from a vertical line. And the area vector is vertical in this particular case. I should label that. The angle between E and a perpendicular to the plane containing the area. The numbers work out to 0.05. As for the units, meters cancels meters, you're left with, you could either call it volts times meters, which is probably the more compact way of writing it, or if instead of volts per meter, you call the unit on E newtons per coulomb, that would be equal to newtons times meters squared per coulomb. Same thing, just a little more awkward to write. This is not given a name of its own. So volts times meter. When we get later in the course, when we get to magnetic flux, the unit of magnetic flux does have a name of its own. But the unit of electric flux, you just have to do that. Okay, so for anybody who's watching the recording, does that show up? Probably not. Might do better. Actually, that might show up. But, you know, the idea is to stop the recording and work on it yourself. And if you get stuck, maybe you want to stop by my office and pick one of those up. So I'm going to turn this thing off now. And